I'm going to tell you right now that if you don't understand how to do this specific problem, you will struggle on a number of tests in this class. These types of questions come up a lot. So, if you are still struggling after this question, let's practice some more together, okay? So we have a piecewise function, and it tells us that this piecewise function is continuous, but we don't actually know the whole piece of this function, right? We know that this is one piece and this is the other piece, and we know it's continuous, we just don't know anything else about that. So what does that mean, that it's continuous? Well, what we know is that at x equals 2, this function equals this function, right? The output at 2 of this function is the same as the output of the 2 at this function, and that's what makes it, or that's how we know it's continuous. So we can set these functions equal to each other. Okay, we can set them equal to each other and say, okay, we know they have to equal each other, and we know that they equal each other when x equals 2. 3 times 4 plus a equals 2 minus 3. So now we can do 12 plus a equals negative 1. And we can subtract 12 from both sides, and we get a equals negative 13. So for this function to be continuous, this a value has to be negative 13. If this a value is negative 13, then this function and this function are at the exact same place when x equals negative 2, or positive 2. Now we're going to use our calculator to solve this one. The reason we can't use algebra is because if you look at the function, oh, it closed out. If you look at the function and you try to put 2 into there, you'll end up dividing by 0, so we can't do that. So let's just use our calculator. We put the function in, and remember we put parentheses around the entire top of the function and parentheses around the entire bottom of the function. Now we know there's a discontinuity in this function when x equals 2 because it makes us divide by 0. So we absolutely know there's a discontinuity, we just don't know what type it is. We don't know if it's a whole or an asymptote. So let's graph it, and we look at x equals 2, and it looks like there's not a whole there, or an asymptote there, right? It just looks like a regular function, but the interesting thing is it's not going to show you the whole because it's very, 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 very tiny. So this is where the table comes in handy. We use the table to be able to see what's going on in the actual function. So you're going to go to Second, Table, and your table actually is probably going to look something like this. Okay, so we're going to look at this and we're going to just kind of evaluate. Every time there's an error, there's either a discontinuity, or there is a discontinuity. So these are domain restrictions. These are places where either there's an asymptote or there's a hole. And we see right there at 2, yep, sure enough, there is an error. There isn't a hole, it looks like there, but we don't know what's going on either side of that. So we're going to use the table to get closer and closer look. So we're going to go to Second, and then this button that says Window, it's also the table settings. So if you do Second, Table Settings, we're going to start at 2. And this delta table means how much do you want the table to change with each step? Well, 1 wasn't giving us very much information, right? Because there was like asymptote, whole, asymptote, right? So let's go with 0.01. We're going to go with a much smaller change. We're going to go back to the table and we're going to look. Okay, so on this side of 2, it looks like it's getting close to 0.33 maybe. And on this side, it looks like it's on the other side of 0.33, but I'm not quite sure if it keeps going in that pattern. But let's get even closer. So we go Second, Table Set, and we're going to change that table setting to 0.000001, and we're going to start at 2. We have to make sure we start right at 2. So we're going to go to our table and then look at that. This is showing me at 1.9999998, it's at 0.333. At 1.999999999, and then at 2, and then at 2.000001, right? So this is right on the other side, and we can see that it's getting very, 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 very close to 0.33. And if you arrow over, you can actually see the actual numbers. So it's 0.33 and then some change, but we're getting really close to 0.33. So we're going to say that the limit as this approaches 2 of this function would be 0.333. We're going to do 3 decimal places all the time in calculus. After the third decimal place, nobody cares and nobody pays attention to that third, anything after the third, but the first 3 have to be correct. So we would 0.333 on this one.